Okay, today we will start with a new topic on variable reluctance motors. You may be considering that almost all the machines that you generally discuss, you take it to have a constant air gap, right. The length of the air gap is same, which would mean the surface of the stator and surface of the rotor are cylindrical. Okay. Now, the motor that we will now be discussing are those where the surface is not smooth. Okay. That means there are saliency or variable reluctance. Okay. So, reluctance of the air gap varies with the position of the rotor, okay, and or the position angular position with reference to any point. Okay. So, if you pass through the air gap through 360 degrees, the reluctance will not be same. That means air gap length will not be same. Is it okay? Now, you are aware that like typical DC machines, you have a salient pole, isn't it? DC machines, you have salient pole. Your synchronous machine also, you have a salient pole in the rotor. So, they all create a variable reluctance. Okay. But they are inevitable type of arrangements, because you need to put some field windings. So, you put this type of a configuration to place the field coils. Next is, now what we want to do is deliberately you create a variable reluctance. The idea is to generate a torque in such a way that the rotor aligns with the stator. Okay. You know that if the rotor is a variable reluctance, if stator is excited, then rotor will move to align with the stator field, because like a bar magnet will move till it aligns with the stator flux, isn't it. So, that is the basic principle of the so called variable reluctance machines. Okay. And typically they are also called as stepped switched stepper motors, where you can move in steps also. You pass pulses in the stator and the rotor aligns, so you can move in steps. Maybe in robotics or pulse movements or actuators or servo drives, you may like to move in steps. Supposing you want to control the arm of a auto transformer or a variac through certain angles, okay, then you can make it to move in steps. Okay. So, the two types are called stepper motors as well as the switched reluctance motor. That means, nowadays the one of the facilitator of this is power electronics. You can switch at high frequencies the windings through the high power devices or IGBTs or MOSFETs or switches. Okay. Now, if you can switch them, so what you do is, in the stator only you put the coils, you do not put any coils in the rotor. Rotor is unexcited. Okay. Rotor is not excited, only stator has the coil. Now, whenever you excite one stator coil, then the rotor will move to align with that stator field, right. Now, you switch another coil which may be displaced with the first coil, then it will move with rotor will move to align with the next coil. So, that way you have a movement. If you go on switching at very high frequencies, then the rotor will continue to move, trying to chase the fields of the stator. That means, you can change the frequency of the switching and you can therefore change the speed of movement of the rotor. Okay. And this is the basic principle of the so called switched reluctance motor as well as stepper motors. In fact, one of the places where original work was done was at University of Leeds in England, and Peter Lawrenson was considered to be the pioneer in development of these switched reluctance and variable reluctance motors. Because I happened to meet him in 1976, we had a meeting in lunch, and at that time they were mostly working on stepper motors. Okay. Then at that time I asked him, stepper motors are low power, maybe a few watts, etc. Then I told him, do you anticipate that this will go to higher levels of power, maybe 100 kilowatt and so on. Then he was very optimistic, yes, I can make a bigger stepper motor, and we are waiting for some development in power electronics, and then it can be done. So, obviously, his sort of vision had come through later, and we have in this so called switched reluctance motors, which are can now be, which are now even built in several hundred kilowatts, okay, to compete with other conventional variable speed motors like induction motors and DC motors and so on. Okay. So, the present trend is you require adjustable speed drives or a variable speed drives or variable torque drives, either you have induction motors, then competing with these permanent magnet motors as well as switched reluctance motors. So, these are the three which are competing, and of course, the people who are working in this area are also competing to make money through proper value addition to their research, etc. Okay. Now, one thing before we go to the actual discussions, let me see if you can have a look at this model actually. Okay. Here you have 8 poles in the stator, right, 8 poles in the stator, and the 2 poles opposite will have the same coil windings, they are in series. So, they carry the same current. Suppose that means this pair when it carries the current, okay, then next will be this carry the current, then next this will carry the current, next this will carry the current. So, that you have 4 coils and their terminals are brought, you can have yellow coil, the green coil, the blue coil and the black coil, okay, 4 coils, right, and they can be excited one at a time. So, you need a switch, 4 switches, okay, for the same DC, your supply is DC. Okay. Supposing you switch the yellow coil, now the magnetic field will be aligned this, okay, and then what we do, we have a this rotor will align with that, okay, a rotor will align with this coil, okay. Now, you tell me what will happen if the green coil is excited now. The green coil is excited, rotor will try to align with that green coil, isn't it. So, the green coil is here, so it will move like this, okay, it will move like this, right, it has to be, rotor will align with it. Now, if I blue coil I excite next, if I excite the blue coil, then where will it move? So, it will move like this, okay, and then I excite the black coil, right, how much it will move, right, it will again move like this, and you will see the angle of movement will be decided by the, it is like a Vernier principle in a way, right, it is the angle between the differential angles, okay, what is this axis and this axis, it is not, it will move by the exact angle. So, you will notice that while you are moving in this sequence, right, you are moving from say yellow coil, green coil, blue coil and black coil, but actually it is moving in the other direction, okay, right. So, if you go the other way around, it will move in the opposite direction. So, you can change the direction by the appropriate switching, and you can change the speed by the changing the switching speed. Okay. So, this will go on rotating, and rotor no coil at all in the rotor, rotor is just a variable reluctance. So, it is called a doubly salient structure, there is saliency in both stator and rotor, right, this is a doubly salient structure, okay, and this will move, and there is a considerable air gap here. Okay. Now, you will also notice how a torque is produced in these machines. What is the principle of torque development? What is the principle? I mean, principle is the old principle of physics of trying the iron tries to get attracted to the magnetic field. That is the very primitive principle. Now, as a matter of energy conversion principles or electromechanical energy conversion principle, so what is the theory behind this? One thing you know is that the inductance of these coils are not constant. Is inductance constant? Each of the coil is the inductance constant, right? Why is it not constant? Variable air gap, because for different rotor position it will have different inductance. Okay. Now, you will have, for example, at this point this yellow coil will have maximum inductance because its rotor is aligned. So, it is called aligned inductance, right. So, there is one value of called aligned inductance. Okay. Then if you change it, it will give another worst position. He is like this. Have you seen? The other position is the inductance will be, is it maximum or minimum? Minimum, it will be unaligned inductance. Is it clear? So, there is one aligned inductance and another will be unaligned inductance. Okay. Now, the other thing is, so the inductance is a function of the rotor position. This is one thing you have learnt from now. Okay. Inductance of each of the coil is a function of rotor position. So, you can write L1, L2, L3, L4 as function of theta, okay, and all the inductance will not be same at the same time, okay, because when this is aligned, another may be unaligned. Okay. Now, the geometry of this machine is very critical. You will notice, for example, this is the angle of the stator tooth and this is the angle of the rotor tooth. See, this angle is here is approximately 20 degrees. This angle is 20 degrees and here it's, I think it is 29 degrees for this configuration. Okay. Now, you have, and please note that number of poles in the stator and rotor must be different. This is the only machine where it must be different. In all other machines we were told that number of poles in stator rotor should be always same in all other machines. So, what is the difference? This difference is this is a absolutely condition that they must be different. Here is a 8 stator and 6 rotor and you can have different combinations. Okay. You understood this now. Now, another thing, see, if you have a is aligned, say, okay, you pass a current through the stator, okay, you pass 10 ampere current, 20 ampere current, 30 ampere current, 40 ampere current, 100 amperes current. Will the inductance be same? Will the inductance be same? Huh? Will it? No, I have kept the theta for the same position theta. I vary the current. Will the inductance be same or not same? Huh? No, it will not be same because there will be magnetic saturation. See, what is inductance? Is the flux per unit current, and flux per unit current is not same because if you increase the current, flux will be less due to saturation. So, if it is aligned, it will be subjected to saturation because in the aligned position there is more iron in the flux path, the more iron in the flux path in the aligned position. Okay. If unaligned, it is more air. Suppose it is here, unaligned position, it is not so much depend upon the current. So, this will be more a linear relation will be there with the flux and current. Therefore, so what you learn now? You learn that inductance is a function of position and induction is a function of theta more when it is aligned than when it is unaligned. Okay. So, you have all the inductances will be there. Okay. Now, you know what is the energy stored in this air gap? Assuming that iron is infinitely permeable, what is the energy stored? What is the energy stored? In the air gap? What is energy? Right, it is there. When once you pass a current, energy is coming. What? what is the energy stored if there is an inductance? Half Li square, right. So, this will be half L1 I1 square plus half L2 I2 square plus half L3 I3 square plus half L4 I4 square plus L1 L2 I mean I1 I2 L1 2, all these things are there. So, you know that what is the energy stored if there are 4 coils, okay. If that is the energy stored, what is the torque? Then the expression of torque in terms of energy stored. You must have studied in electromechanical energy conversion principles. Is a dW field by d theta, isn't it? dW field by d theta is the torque. That is torque. So, you know what is the mechanical torque by knowing the inductance profiles, and therefore, if the torque will be I1 square d L1 by d theta plus I2 square d L2 2 by d theta, because it is partial derivative with reference to current, with reference to theta by keeping the current constant, and this is called co-energy, right. This co-energy, when you have done when you studied the modeling, this is what it is, right. So, you have got the energy stored, etc. So, the principle of energy conversion or torque production is for which you need to know the inductances and their variation with theta, variation with I, then you find out the torque is differential of inductance with reference to rotor position. Okay. So, if the rotor position there is no differential, when dL by d theta is 0, there is no torque. Okay. Now, it is a product of current into gradient of inductance, right, current square into gradient of inductance. So, torque is produced if current square is positive, which is always there, and gradient is positive. If gradient is negative, it will give a negative torque. So, you can make a motoring or a braking. You can make, so you pass a current when gradient is positive, you do motoring. If you pass a current when gradient is negative, you do braking. This is another factor. Okay. Now, this inductance gradient you have to know. So, you must pass a current at right time of the rotor position, right. You can't pass current as you like, this is another problem. So, the switching instant is depend upon rotor position. Therefore, you must have an electronics to detect the rotor position. Therefore, another important thing for this machine is that the rotor position sensing is important. You must sense the rotor position, right. So, you sense the rotor position and then pass a current through that. So, you need to have a processor, right, and this machine cannot work without a controller, whereas a DC machine can just put it to the supply. You can't put it to the supply. If you put it to the supply, nothing will happen except the winding will get burnt. Okay. Therefore, you need a black box or a controller between this, right. So, these are the broad thing I have explained through this model. So, I assume that you have learnt everything about switched reluctance motors. Okay. Now, we will go to see what are the details of this switched reluctance motor now. Okay. Now, the features are, I am repeating this, whatever I have written, I have told, maybe it is written here. So, it is a important futuristic variable speed drive system. Why we are telling it is futuristic? Because lot of things have come to the practical applications. Okay. And it is a high power stepper motor. It is stepper motor, but high power. Okay. And as of now, up to 200 kilowatts have been built, because people now say they have gone even higher, and built on a 250 frame. What is the meant by 250 frame? This is a frame number. I told you the frame number is the millimeters of the center height from the base. It is a 250 millimeter frame, and it is TFC frame, is totally enclosed fan cooled. TFC means this is the one. Okay. And so, it competes with what? Because after all, today's technology is competition. Okay. Competes with converter fed DC motors, because the variable speed DC motors are still preferred in some cases because of the quick response, and of course, inverter fed AC drives, basically variable frequency induction motors, which will be either vector control or direct torque control. Okay, nowadays there are these are the things which are there, adjustable speed drives, and these are multipole wound stator and unwound rotor. What is construction is, stator has multipole and stator is wound, whereas rotor is toothed, but rotor is brushless, but it is unwound. Rotor is unwound, brushless. This is one other thing. So, cooling, there is no loss in the rotor at all. You see, no current in the rotor, no loss in the rotor, no core loss in the rotor, no copper loss in the rotor. All losses in the stator, all you have to do is to only stator gets heated, okay, and rotor does not get heated. Then the power electronic controller, it has to be interfaced. You need a power electronic controller to switch the DC supply to each of the windings, okay, interface between motor and supply to inject. Okay, why do we need the power controller and supply to inject pulse of current to stator windings. So, you pass a pulse of current, and how much current it will flow depend upon the circuit parameters of resistance, inductance. Okay, when once you pass a 100 volts current, 100 volts voltage, it does not mean it will give a nice 100 volts current if it is 1 ohm resistance. So, it will go through its own step response. Now, it is different than stepper motor in some respects, okay, the switched reluctance motors. Okay. This switched reluctance motor is designed for efficient power conversion at high speeds, okay, comparable with those of the permanent magnet brushless DC motors. These are supposed to be more efficient compared to PMBL DC, but of course, this is being debated, okay, because brushless DC also has very good efficiency. Okay. The stepper motor on the other hand is usually designed as a torque motor and limited speed range. Stepper motor is not a continuous speed one, it is only rotates few revolutions or a few steps, okay, and it is a torque motor, it does not give you speed, it gives you torque. Okay. This you are concerned more about that. Okay. Now, the features that are claimed on SRM is low cost, because it easy to make, hopefully the rotor is just a unwound one, and it can be a constant torque, you can produce a constant torque independent of rotor position, okay, and then desired, you can fix a desired operating speed, you can run at whatever speed you want by adjusting the switching, and you can have high efficiency, and it has a large torque to mass ratio. Usually one of the design feature is it must produce maximum torque with minimum mass. So, it is called a torque to weight ratio. Okay. And what are the advantages? Advantages are, as I said, it is a simple rotor and very few manufacturing steps. If you use a wound rotor, then you have to have lot of manufacturing process involved. Then it has low inertia and it has a quick response. Okay. This is it can respond quickly, and stator is simple to wind, because all you have is, you do not have several coils, all you have to do is put one coil, put it in one pole, you have seen that. Therefore, then there are very short end turns are short, you just a coil, just place it on the pole, right, no complicated end windings, right, and there are no crossovers. In large induction motors, there are crossovers of the winding, because they are all overlapping windings. So, one overlaps the other. So, the end winding at the end they overlap, okay, the crossover will be there, right. So, you have to be careful in winding them actually, okay, because what you are doing, your coil is having a planar surface, but your rotor is having a cylindrical surface, okay. So, your solid geometry will be useful in the winding of these machines, okay. Now, bulk of the loss appear in stator, we know in switch reluctance machine most of the losses appear in the stator, and which is easy to, in stator it is easy to cool, because rotor losses mean it is difficult to cool. Okay. Now, there are no magnets unlike in a PM machines. So, easy to fabricate, if you have magnet, there are difficulty in fabrication, you have to magnetize it, put it, and the magnets may also affect your other parts in manufacturing. Okay. Therefore, then temperature problem is not there, magnets properties are sensitive to temperature. Okay. If high temperature, it will affect the magnetic properties, right. So, absence of magnets, maximum temperature, you can run it at higher temperature. Okay. Now, torque is independent of phase current, so reduce semiconductor switches, therefore, the number of switching can be reduced, right. You can make the torque, because it depends upon torque is I square into dl by d theta, you can make it also independent of the current. High starting torque possible without excess inrush current. You can have, this is one of the claims, it can provide very high starting torque. Okay. All you have to do is, because you have a limitation of starting torque in other machines. Okay. Then you can have a very high speed, because most of the other machines have limitations of speed, synchronous induction, DC, etc. And there are no brushes, so you have no problem of brush contact, etc. And you can also have a torque speed characteristics which is tailored to the application, because different application require different torque speed characteristics. So, SRM you can make it as you like about the characteristics. So, we find, so these are some of the advantages claimed for SRMs, okay. And all machines do not have only advantages, right. Okay. There will always be disadvantages. Okay. Now, disadvantage is your torque is not smooth, you have pulsed or a non-uniform torque. So, there will be torque pulsations will be there, okay, because it is like a bang, you are going, whenever you pass a current there will be a torque, then you switch it, during the process of switching there will be the problem of torque being varying. Okay. So, torque ripples will be there, okay, and it will also make acoustic noise, all these things, because high frequency switching and the acoustic noise is an issue. Then there will be torque ripple and current ripples in the supply. So, once you pass a current from a DC supply, the current is not going smoothly out of your DC source. Of course, the DC source does not come from a battery invariably, it is a rectifier anyway. So, your DC will pass a pulsed current that gets reflected on the AC. So, the AC current will have harmonics, is not it? You can try to filter it out. So, there are power quality issues, right. So, it tends to be large, and DC supply, the current ripple current is high, it is not a smooth current, and then you require a large filter capacitance to smooth out these things. Now, there will be lot of AC line harmonics, okay, there will be, and in systems, because we have, so AC side there will be harmonic currents, right. Now, another disadvantage, you can't directly use it with the mains. If I just give a DC or AC supply, I give a SRM, you can't use it, you require a controller. So, it involves a controller which itself is a involved process. And another problem is it is not standardized as of now, because there is no standard motor, okay. And applications where they have found it useful, this switched reluctance motors, they have found it useful in the industrial drives, they are being used, general purpose and systems and general, then mining equipment they have applied, actuators, industrial DC motor replacement. Whenever they have DC motors gone bad, so they will replace with they have tried to replace SRM as a variable speed drives, okay, which we call it retrofitting, okay. Then they have tried to use in electric trucks, fans, both commercial fans, industrial fans, compressors, centrifuges, ultra high frequency metal processing, high performance metal processing, metallurgical application. Automotive auxiliaries, means stepper motors, you can use it in automotives, both as main drives or auxiliary drives. Application then application specific centrifugal load drives, high performance automotive actuators, again fans in automotives and industrial drives, food processors, hand tools, vacuum cleaners, textiles, vehicle propulsion, then spindle drives, then washing machines. I think they have found applications. Of course, only last 10 years have seen a very keen competition between SRM and PM machines. But at present PM machines seems to be, because of better materials, PM machines also seem to be favored. Okay. Then of course, in stator you have, construction wise we already know stator has multi-poles construction, and the typical construction will be, you can have stator 6-4 means stator 6 and rotor 4, okay. Then 8-6, okay. Then controller, then you can have, you can switch DC voltage to coils in sequence. What the controller does? You switch the DC voltage to coils in the sequence, okay. Now, it is a doubly salient machine, that means both sides must be salient, or okay, none of them are cylindrical surfaces, okay. Then salient poles are both the stator and rotor with phase coils mounted around diametrically opposite stator poles, isn't it? We have seen diametrical. So, it is not, if I have 8 poles, 8 are not independent, it is basically 4 phases, 6 poles means it is 3 phases, okay, and 4 poles will be 2 phases, okay, and 2 poles means 1 phase, there, that is what it means, right. So, they are diametrically opposite stator poles, okay. No windings in stator, rotor, rotor has no windings, and there are no magnets in the rotor or no cage windings, okay, but it is built up of stack of salient pole laminations. Basically, whatever you, it, they also are laminated because again you have to prevent some eddy currents, etc. Okay. So, it is not solid rotor incidentally. Okay. Okay, let us see how it works, right. So, it is rotating, right. How many poles are there in the stator? So, it is a 3 phase, 6 poles. So, you will see that these 2 poles is one and these 2 is another, these 2 is the third phase. How many in the rotor? 4 poles on the rotor. So, it is, as you switch the coils here, you will see it is rotating, okay, right. So, that means these coils, these are the coils, red ones are the coils wound on these poles, you see these poles, right, and you will they will just be rotating as you excite each of these ones, right. I think you are aware of how it rotates. It is basically, it tries to align with each of these poles, okay. Is it clear? You have seen it rotating, okay. So, this is a static picture. So, you have how many, now what is the poles? 8 by 6, it is the same as this one, okay, same as this 8 by 6, right. And again you have this will be, if you have, this is phase 1, then phase 2, then phase 3 and phase 4, okay. And this is the rotor, and is aligned, rotor is aligned with which phase now at this position? Phase 2, right, and phase 2 it is aligned. That means, the phase 2 will have maximum inductance at this position, okay. And which one will have minimum inductance in this position? Which phase will have minimum inductance? So, phase 4 is unaligned, this is aligned, this is unaligned, okay. This is unaligned, okay, and others are in between. See, there is some overlap angles, you see, this is fully overlap, this is partly overlap between stator and rotor. So, flux lines will be going like this, this is almost no overlap, this is also partly overlap, this is fully overlap, right. So, you will see that each of the phases will have a different type of a interaction with the rotor poles, okay. And in this air gap there will be the energy stored, and the energy with reference to rotor position is the torque, energy stored with reference to rotor position is the torque, okay. So, you have got and we have already said inductance of this coil is maximum, inductance of this coil is minimum at this position, and if you pass a current through this, inductance will vary because of saturation here, because this is highly saturated, because it is a totally iron piece, very limited air. See, when do you find saturation? You find saturation if the magnetic path has more iron, saturation iron only, okay, not in air there is no saturation, right. So, here there is, and in this inductance unaligned there is no saturation, it can be considered to be linear, it does not depend upon the rotor stator current or the winding current, okay. Is it clear? Any doubt till now? So, we have cleared the construction, requirement of switching, inductances, inductance profiles and other things, okay. It is not done, you think about it, you can have more, yes, it has to be differential, okay. You just reverse this and think, okay. What I suggest is you have 6 and 8, you can have, okay, right, and see how it works, right. So, the combinations generally are these 6 by 4, 8 by 6, 4 by 2, that means stator 4 rotor 2, 6 by 2, 10 by 4, 12 by 8, 12 by 10. So, these are all the stator poles and these are all the rotor poles. So, these are the combinations which are used. So, you have these different combinations of the machines, okay. What is the first one? So, this is a 4 by 2 machine, okay. It is 4 by 2, no, 2 rotor poles. So, it is rotating as the stator is switched, okay, clear, okay. And this, then next is, this is what is the combination here? 4 by 4, still it works? Not possible. What is happening? Huh? 2 phase motor. Huh? Huh? Animation is there. Huh? This is 6 by 4. This is possible. Okay. I think there is a fallacy here. Okay. Okay, you have to pull it out when it is aligned. Okay. Then this is the one what we have shown, 4 phase motor. This is a single phase motor. Okay. Then 2 phase motor. I mean 2 phase is okay, but the rotor, that's the thing we have to see. This is a 3 phase motor and 4 phase motor. Okay. Huh? First one is 2 phase. Yeah, it can't be single phase, is it? Huh? Okay, I think there is a fallacy. Maybe we have to remove one. Okay, good you identified. Is okay? You know they are animated and they are rotating also. Okay, okay, right. Okay. So, other thing is you have poles are wound diametrically opposite in pairs to form. This again we have already mentioned this. Each phase when excited produces a pulse torque on each passing rotor pole. So, when on some one pole is excited means it will produce a torque on the rotor, okay. It will push it to align, okay. Then all the 4 will push. So, the net torque will be T1 plus T2 plus T3 plus T4, because each of the coil excitation will push, but at any one instant there will be only one coil excited, there will be only one T1, okay. So, you have a T as a function of theta or time, okay. Yeah.
As we are doing in stepper motor, we can use micro stepping. Means simultaneously energizing two phases. Can we do it here? Because for example, if you are
Yeah, if you energize two phases, the magnetic field will be a resultant of this, and it can, you can do it also, but it is generally not done because it will complicate your controller. Okay.
because sir, if we do that, then the torque precision will minimize then.
Yeah, that is true. But then since you are working at high speeds, then you have to see what the possibilities of this thing. Okay. Now, usually step angle, how much step it will go or per stroke. See, for per stroke means per each successive switching how much angle. Okay. Uh, this is a one formula. It is 2 pi by q n r, where q is the number of phases. Okay. So, that means if q is 4, rotor poles is 6 in this case. So, the angle will be 360 by it will be 15 degrees. Okay. So, the angle that will shift per each stroke will be 15 degrees. So, okay, and similarly, so this is a simple geometrical calculation. Okay. So, now the thing is, if the fringing is neglected, what is fringing? Flux does not go through the iron, but it just escapes through the air. Fringing is different than leakage, isn't it? Yeah, fringing is in traffic. You may see some fringing. Do you see some fringing when somebody is going? He suddenly finds a path available, in some bylane. He suddenly fringes into the bylane. There is usually somebody going in a scooter in a normal lane are there. He suddenly finds some cut over there. Suddenly to the left there is some bylane going to go to faster and jump the red light. So IIT hostels also, outside there is some bylane is made. Okay. So you may have that's fringing. Okay. So, fringing is a natural phenomenon of the flux. Whenever you find some alternative route, you do fringe. Okay. So, it do not go through the iron. So, if the fringing is neglected, there must be overlap between a pair of rotor poles and the poles of the excited phase. Okay. So, torque angle can be produced through, in this case torque can be produced through an angle beta. Okay. Beta is the step angle. Okay. To produce unidirectional torque through 360 degrees. Now, this the angle beta, that is the stepping angle of the arc angle, must be more than the stepping angle, okay, because they are overlap angles. Okay. See, this is the beta r means rotor tooth angle. Okay. This is beta s is the stator tooth angle. Okay. These are because as we mentioned here, in this the beta s is 20 degrees and beta r is 29 degrees or something. Okay, in this one. So, in order to get largest possible variation of phase inductance with rotor position, interpolar arc of the rotor must exceed the rotor pole arc, right. This is the interpolar arc and this is the stator pole arc. Okay. Because then there must be a gap. So, you expect this one should be more. So, a further constraint on the pole arc is that beta s is made slightly smaller than beta r. see this is beta s and this beta r, it is generally small. Okay. These are some of the design considerations. Okay. Now, the motor is doubly salient with phase coils mounted around diametrically opposite stator poles, it is again repeat. Energization of a phase will lead to the rotor moving into alignment with the stator poles. So, what is the principle is minimizing the reluctance of the magnetic path. What is the principle? You minimize the reluctance of the magnetic path, that is the principle. Okay. Now, we have already seen the reluctance of the circuit decreases as the rotor aligns with the stator pole. Reluctance decreases as the rotor aligns with the stator pole. When the rotor is aligned with the stator, the gap between the rotor is small, this we have already seen. Okay. And the rotor forms a magnetic circuit with the energized stator pole. So, what you have is once you energize a stator pole, you have a magnetic circuit calculation, that is all. It is a magnetic circuit with an MMF being produced by the stator and the rotor forming a magnetic path only. So, so magnetic path will be both stator core, air gap, rotor core and all the things. Okay. So, you create a magnetic path, so it is a magnetic circuit calculation. Okay. So, reluctance of a magnetic circuit is the magnetic equivalent circuit of resistance. So, you know how to calculate the reluctance. Reluctance is sum of the reluctances of both iron and air. So, you calculate the reluctance. Okay. Okay. Now, at aligned position, reluctance is minimum. This is where the name switch reluctance. Okay. You switch the reluctance. Okay. So, here is it aligned or unaligned? This one is. So, aligned, you see this is the flux path, this is the flux goes nicely and it divides into two paths, right. Okay. So, if this is excited, okay, that is what happens. Okay. While this is excited, what is the flux path is not the same as this. Aligned means the iron goes here, so it will follow certain path like this. So, the flux, so you can do a finite element analysis for each position and calculate the inductance, etc. Okay. Is it clear what is meant by aligned and unaligned inductance and flux paths? Flux paths are different. Okay. Right. Now, we are increasing the current. Okay. So, it is 100 amps. What is happening? Okay, now 20 amperes, right? You see here 70, 80, 90, 100. Okay. So, so the current is going up and so for as the current goes up, flux goes up, right. So, for the same position, for the position theta, so this is position theta. So, for a given position theta fixed, this is the variation of flux linkage with current, psi is the flux linkage with current. Okay. Are you seeing it? Is it clear? Anybody doubt on this? So, I have fixed theta, rotor is fixed at a position theta, I am only changing the current in the stator. As the current in the stator increases, the flux increases, okay, but it is linearly increasing because it is in the unaligned position, more air than iron. Okay. So, it is more linear here, okay, more linear. So, what will be inductance? Is it varying or constant? That is inductance is slope of this psi I curve, slope of psi I curve, is not it, right. So, you have a, what is the inductance will be d psi by di, right. This is the inductance, that red one as you see here. Okay. So, this is just a minute. Okay. So, you have psi and I, this is the flux linkage versus current, it is linearly changing for the given position theta. My position is theta. So, psi is varying with I and this area we call it as energy stored, is not it, and this area we call it as co-energy W dash. you are aware this is energy, co-energy, energy plus co-energy psi into I. Okay. Now, this slope is L, which is psi by I. So, you find this area, you call it as the co-energy, and this area you call it as the energy, right. This you are aware of, magnetic field. Okay. So, what is the torque? Torque is dW field by co-energy by d theta when current is constant. This you are aware, this is the basic equation of energy conversion. Okay. This is the co-energy, and of course, other is dW field by d theta when the psi is constant. Both are the ones you are aware of. Okay. So, this is the developed torque in terms of co-energy or field energy. Okay. Because what is energy, co-energy is psi di 0 to I. Okay. So, W field is 0 to psi I d psi and psi is Li, and W dash co-energy is equal to field energy is half Li square. Half Li square is only when you have these two only linear region, only then these are equal. So, torque is half I square dl by d theta. So, when you know L for a given theta, what is the torque you know for this. So, this is a simple way to calculate. Okay. Okay. Now, we go to the other is torque inductance profile. Okay. Just another 2 minutes we will finish. So, we observe the flux linkage variation with rotor positions theta 1, theta 2, theta 3 and excitation in a phase is varied. We observe that inductance variation when rotor is free to rotate from position with constant excitation in a phase. Okay, let us see. Okay. Now, let us see. Now, this is one unaligned, linearly varying at theta 1. Now, I have changed theta. Okay. It has gone nearer to aligned, and currents are same range. For the same range of currents 0 to 100 amperes, what is happening? At theta 1 it is linear, and at theta 2 it is non-linear because there is more iron in that path. Okay. And at theta 3 which is aligned, fully aligned, it is more non-linear, but see, you will see, is it clear? So, you have a family of psi I characteristics for different theta, family of psi I characteristics for different theta. Therefore, what will happen to co-energy? Co-energy will increase, more co-energy in aligned position than in unaligned position, same current, this one thing. So, there is a different area of the, so this is one observation we have. Okay. So, theta 1, theta 2, theta 3, there will be a there. So, torque will be different. Okay. I hope you are able to, this has made you clear. Okay. So, it is changing. So, you have a variation, psi is a function of current and theta, psi is a function of current and theta. Okay. Right. And okay, now you see this. What is the flux pattern? Link rotor position. Okay. Rotor is moving. Rotor is moving slowly, but the flux, you see, now it is aligned, maximum flux, then it is moving, then you have a almost minimum flux. Okay. Right. So, you will find that different, here this is excited. Okay. Now, let us see, now this has aligned, now it has come to maximum flux. Okay. Right. So, flux linkage rotor variation with rotor position, you can see how it is varying, and you will have a different position. Okay. Okay, this is what? Now, rotor is free to rotate, okay, theta 1, theta 2, theta 3. So, you have these inductances. So, excitation, so 100 amps I am fixing. Now, this is theta 1, theta 2, theta 3. So, the angles are changing, okay. This is observation you have, right. So, your co-energies go on increasing for the same current, okay. So, as the rotor, what is this, okay. So, you find that this is L aligned, unaligned, this is aligned. So, what this is more, now the inductance will be the slope of this aligned and this in between, is it clear? Okay. So, as the rotor rotates, the inductance varies between two extreme values as the rotor rotates, okay, unaligned and aligned. So, minimum inductance is unaligned, maximum inductance is aligned, which is saturated, okay. So, fringing results in sharply, okay. So, the neglecting fringing results in sharply defined corners, etc., okay. Okay, I think we will discuss the remaining things in the next class, okay, and we will close it here, okay.